In this video, I'm going to talk about how to work stoichiometric problems. Stoichiometry is math interlaced with chemistry. You have a reaction going on, you have reactants and products, and with a stoichiometry type problem, you will be given information about one thing in the equation, and you have to find out information about something else. In order to do this, you need a balanced chemical equation to be able to solve the problem. Every type of stoichiometric problem has what's called a mole ratio step. And in this step, you use the coefficients of the balanced equation. So you must have a balanced equation in order to work the problems. Problems may be mass volume problems. They may be volume mass problems. Mass mass, moles mass, mass moles. All of those are stoichiometry. In a mass mass problem, for example, the first word, mass, is what you are given in the actual problem, and the last word, mass in this case, is what you are being asked to find, the mass of something else. For example, you might be given the mass of a reactant and asked to figure out how much product can be made. Or you might be given the mass of one reactant and asked for the mass of another reactant needed to react with it completely. It doesn't matter which side of the arrow the given and the asked are on. That's one thing you don't need to worry about. They can both be on the left, both be on the right, one on the left, doesn't matter. You work the problems the same way. There are basically 3 steps to solving a mass problem, and all the other types of problems that I mentioned in the beginning are all basically shorter versions of a mass problem. So we'll talk about those at the same time. The first step is to have a balanced equation. So if you are given a balanced equation, you can skip this step. Otherwise, you need to write an equation and balance it in order to be able to solve the problem. The second step is to convert whatever you are given into moles. So if you're given grams, you're going to convert grams to moles. If you're given volume, you're going to convert volume to moles. Whatever you're given, change it into moles. If you need help with this, I have a video linked down below in the description that can help you out with this. Once we have moles in the second step, we're going to convert moles of what you were given information about to moles of what you are being asked for. To do this, we use the coefficients from the balanced equation. This step is always in the problem. That's why we require a balanced equation, because you always have this step. You might not have step 2, because if you're given moles to start with, you don't have to do anything. It's already in moles, so you get to skip that step. You never get to skip step 3. Once we do step 3, we will have moles of what we were asked to find out about. If you're asked for moles, you're done. But if you're asked for grams or if you're asked for volume, then you have to do one more step to convert the moles to whatever unit you are asked for, be that grams or volume. So if it's a mass problem, that means you're given mass in grams or kilograms, and you're going to have to convert that into moles. So you'll need to do step 2. You always need to do step 3. And step 3 will change it from moles of the thing you were given to moles of the thing you are asked for. And then you'll need to do the last step to get the moles to grams, since that's what it asked for in the problem. If you have a mole mass problem, that means you were given moles. So you get to skip step 2, because because step 2 says convert your given into moles. Well, you were given moles. So you only have to do steps 3 and 4 mathematical steps. You always need to do step 1 because you need those coefficients for step 3. So a mole mass problem, you would need steps 1, 3, and 4. A mass mole problem means that you are given mass, grams, and asked for moles at the end. You'd balance your equation. You would convert your given mass, grams, to moles. You would work the mole ratio step to get from moles of the first thing to moles of what you're asked for, and then you're done because it's asking for moles and you get to skip step 4. So step 2 depends on what you're given. If you're given moles, you get to skip it. And step 4 depends on what you're asked for. If you're asked for moles, you get to skip it. Let's work some example problems. Here's our example problem. If 10.5 grams of propane, which is C3H8, are burned in a grill, this is the stuff that you, when you turn on the gas on your gas grill and fire it up and cook some burgers, this is the gas that you use. How many grams of carbon dioxide are produced? So the first thing we need is an equation, and we're being given grams and we're asked how many grams. So this is our final answer, needs to also be in mass. So this is we were given mass, we're asked for mass at the end. So this is going to be a mass problem, which is going to require all of the steps we talked about. So first we need an equation. So we have C3H8. In order to burn a hydrocarbon like this, it requires oxygen. And the products of a combustion reaction are always CO2 and water. So the first thing we need to do is balance this. Assuming that we have one molecule of propane here, that means we have 3 carbons, so we need to get 3 carbons on this side. It also means we have only 8 hydrogens on this side, because that's the only place hydrogen appears. So we need to get 8 over here, but it's H2, so we have to put a 4 in front because 2 times 4 is 8. Now we have 8 hydrogens and 3 carbons. So this part is fine. Now we have to figure out oxygens. We save them for last because it's in 3 different things. To balance oxygen, we need to add up all the oxygens on this side because this one already has our coefficients locked in. So here we have 3 times 2 is 6 oxygens. Here we have 4 times 1 is 4 oxygens for a total of 6 plus 4 is 10. We need to get 10 on this side. If we put a 5 in front of this, 5 times 2 is 10, and our equation is balanced. In our next step, we need to convert our given, which was 10.5 grams, into moles. So we have 10.5 grams of C3H8, and we need a conversion factor to change this into moles. 1 mole of propane will have a mass we have to calculate from the periodic table. So carbon has a mass of 12, and we need hydrogen, which is basically a mass of 1. So we have 3 times 12 is 36, plus 8 for our hydrogens is a mass of 44 grams. So grams, that unit, not the number, just the unit, cancels, And we are left with 10.5 times 1 on top, which is 10.5, and our unit is moles. And on the bottom, we have 44 grams, but the grams canceled, so it's just 44. 10.5 divided by 44 is 0.2386. I'm going to keep an extra place there. The next digit is a 3, so I'm going to go ahead and cut that off. And this is moles. I want to keep more. I have 3 significant figures in my beginning number, so I'm going to keep 3 at the end, but I don't want to round off in the middle or I'll get a round off error introduced into this. So I'm going to keep more than I need until the very end of the problem. For our next step, we're starting with what we have at the end of step 2. So we have 0.2386 moles of C3H8. It's important to keep your labels on these because it's easy to get confused if you don't. We need a conversion factor here. This is our mole ratio step, and we're going to convert from moles of what we were given, propane, to moles of what we were asked for, carbon dioxide. So since this is on top, we want to cancel that. It's going to have to go on the bottom. Moles of propane on the bottom so that that unit will cancel. And moles of what we're trying to find on top, which is our CO2. Now the numbers that go in front of this, remember this number here came from the periodic table, but these numbers come from our balanced equation. So if we look back at our balanced equation, the number in front of propane, in front of C3H8, was a 1. So we're going to put a 1 there. And in front of CO2, this coefficient is a 3, so we're going to put a 3 right there. This unit cancels, and we end up taking our moles of propane times 3 divided by 1, and that will give us our moles of CO2. If we were asked for moles, we would stop here, round to significant figures, 3 of them, and be done. But we were asked for mass, we were asked for grams. So we need to do one more step to get our moles back to grams. So our last step, we take the number that we found in the last step, and we want to convert from moles to grams. So we need our conversion factor. On the bottom, we want our units to cancel, so we're going to put 1 mole of CO2. This number has nothing to do with our balanced equation. It has to do with how much carbon and oxygen add up to using the periodic table. So oxygen is 16, 2 of those would be 32, plus carbon is 12, which gives us a mass of 44 grams of CO2 in 1 mole. It just happens to be chance that the top one was 44 and the bottom one was 44. I guess I picked a poor example. That is not usually going to happen. This unit will cancel, and you're going to take your moles of CO2 times 44 grams divided by 1, and we get 31.5 grams of CO2. 3 sig figs. We were given 3 sig figs, so this is our answer. Here is a second example problem. How many moles of oxygen are needed to react completely with 45.5 grams of hydrogen? And we are given the balanced equation. So step 1, we have already been given, and so we don't need to worry about that. So this is step 1, balanced equation. Step 2, get whatever we're given into moles. So we are given 45.5 grams of hydrogen gas. And remember, hydrogen is diatomic, it's H2. We want to change this to moles. So we need a conversion factor. And we're changing it to moles. 1 mole of hydrogen gas. Hydrogen has a mass of 1 atomic mass unit, or grams per mole. And since it's H2, it's going to be 2 grams in 1 mole of H2 gas. This unit cancels, and we're left taking 45.5 divided by 2, which is 22.75 moles of H2. Next is our mole ratio. This is always in the problem. You always have to do this. Notice I kept more digits than I needed there. So we have 22.75 moles of H2. That's our answer from the first part. That comes down here. And our conversion factor, we want to cancel moles of H2, so it goes in the bottom. And we are asked how many moles of oxygen. So we want to put moles of oxygen. So we find oxygen where it's alone, right here. And that's going to be what we're going to look for when we look for our coefficients. So in front of oxygen, there's nothing. We assume that that is a 1. So we're going to put a 1 in front of our oxygen. We got that from our balanced equation. Now, moles of hydrogen, we go to hydrogen gas. There's a 2 in front, so that 2 goes right there. Notice that this is the only step you use the coefficients from the balanced equation. And you notice you have mole over mole, and these two things are different. That's the only place that happens. If you look anywhere else, you have mole and something else, and it's the same thing, H2 and H2, O2 and O2. But this one has an O2 and an H2, so that means we're going from one to another, which means we have to use our balanced equation to do that. So we're going to end up taking our moles. This unit cancels. We're going to be left with moles of oxygen. So we're going to have this number times 1 divided by 2, which equals 11.375 moles of oxygen. Well, we were asked how many moles of oxygen. So we're done. We don't have to do our last step and change it to grams or anything else because we were asked for moles. But before we leave this completely, we have to make sure we have the right number of significant figures. So we go back to our original problem, 1, 2, 3 digits. So we are going to keep 1, 2, 3 digits. So we're going to cut this off right here. And because this is a 7, if it's 5 or higher, we round up the last one we're keeping. So we're going to keep this 11.4 moles of oxygen as our final answer. In our next example, we're going to incorporate volume. For example 3, we are asked to determine what volume of CO2 will be made by the combustion, which is a fancy name for burning, of 2.5 moles of octane. Octane is the stuff that's in the gasoline you put in your car. That's the part that actually burns, that makes your car go. So the first thing we need is a balanced equation. Octane, oct means 8. So octane is C8H18. You always need oxygen in a combustion reaction, and it breaks it down completely into CO2 and H2O. Next, we need to balance this. Here's our equation balanced. Next, we need to convert whatever we're given into moles. But we were given moles. So we get to skip this step because we already know it's 2.5 moles of octane because we were given that. Step 3 is our mole ratio, and that's where we're going to use our coefficients from our balanced equation. So we're starting with 2.5 moles of C8H18, and we need a conversion factor. We want to cancel moles of C8H18, and we want to find CO2. We're asked for the volume of CO2. We'll figure that out in our last step, but right now we've got to get to moles of CO2. So we're asked about CO2, carbon dioxide, so we put that on top. Now we go to our balanced equation to find what numbers go in front. So in front of our CO2 on top, we find CO2, and there's a 16 in front of that. For our bottom, we have our octane. So we're going to go to our equation, find octane. There's a 2 there. So these two numbers came from our balanced equation. This unit will cancel, and we'll be left with moles of carbon dioxide. So we need to take 2.5 times 16 divided by 2, which is 20 moles of CO2. In our last step, we have to get our moles of CO2 to whatever unit we're asked for. In this case, we were asked for volume. So we're going to start with our 20 moles of CO2. We're going to have to multiply this by a conversion factor to get it into volume. At STP, that stands for standard temperature and pressure, 1 mole of any gas, doesn't matter what it is, occupies 22.4 liters. So we're going to use that as our conversion factor when working our last step. If we were given moles to start, we would have used this in our first step to convert from liters to moles, but we were given moles, so we got to skip our first step. Conversion factor. We have moles of CO2, we want moles of CO2. And on top, we want our volume, liters of CO2. And using our conversion factor, 1 mole of any gas is 22.4 liters. This unit cancels, and we end up taking 20 times 22.4, which gives us 448 liters of CO2. We go back to our original problem. Our one given number here was 2.5 moles, 2 sig figs. So we're going to keep the 2 biggest and round this to 450 liters of CO2. Don't just chop off the 8. You need to round up, but you also need to keep the distance to the decimal point. So this would be our final answer to this problem. Please come back and see my other videos. They're listed down below in the description.